I would like to present our speaker, Dmitry Pelinovsky, professor at McMaster University. He will be giving a talk today about smooth and peak traveling Stokes waves. Please, Dmitry, the stage is yours.
Hey, great. Good morning or good afternoon, depending where you are. I feel almost mandatory to give a talk on fluids. I don't work with applications of fluids. I work with applied PDEs and stability of nonlinear waves. But I was lucky that I had an undergraduate student last year, Spencer Locke, and with him we reviewed lots of fluid material, and I think my talk will be something interesting, though it's on a classical subject. I'd like to mention that Spencer just finished his undergraduate degree and he is moving to University of Michigan for graduate study. Don't hesitate to interrupt with any questions. So I will start with some background information, and it is just a classical problem of rotational motion of an incompressible fluids. The problem with a free surface, so-called Stokes wave. As I said, I'm very interested in the stability of periodic or solitary waves. And the fluid mechanics equations, the Euler equation, seems to be a little bit complicated because they combine the Hamiltonian dynamics on a free surface with elliptic PDEs for the velocity potential coupled together. And therefore, the main question is how to get nonlinear evolution equations close to describe this Hamiltonian dynamics. And from very long ago, some applied PDEs were derived in this context, in particular for long, small amplitude waves. So the wavelength is much larger than the depth of the fluid, and the amplitude is much smaller than the depth of the fluid. And of course, the list of PDEs would start with a classical Korteweg-de Vries equation, which is evolutionary equation, first order derivative in time, dispersive here, and convective nonlinearity. And it was derived long ago, and it was used for existence and stability of solitary waves and periodic waves. A different equation was derived not so long ago, only 50 years ago, much shorter compared to KdV equation, and it was a regularized KdV or PBM equation. The only difference here appears to be in the dispersive term. 20 years later, another PDE was derived by Kamasa and Holm, and if you look at the left-hand side, it is just the BBM equation. But it's modified with some quadratic nonlinearity and cubic derivatives here. And in fact, this equation was rigorously justified, as well as all other equations were rigorously justified in the context of fluids. So now I will start my talk with a comparison of the state of the art and the existence and stability theory for periodic and solitary wave solutions for these three equations. For KdV and BBM, they share common features. Solutions of initial value problem exist in the Sobolev space H1. And in this Sobolev space, the energy and momentum functional are well defined. That makes it energy space, which is very good, conserved in time. And the traveling wave solutions can be found effectively from an ODE. And the study of this ODE shows that all traveling wave solutions have smooth profiles in the admissible range of the wave speeds. And moreover, these traveling waves becomes constraint minimizers of the energy subject of momentum. Then by working with Lyapunov theory of stability, we can prove that because this is constraint minimizers of energies, the traveling waves are orbitally stable in the energy space H1, for which solutions of the initial value problem are well defined. And so in this theory, the original theory, there are only smooth waves, while in the fluids, we know in the Euler equations, there are also some peaked waves, or even waves with singularity. And if we look now at what Kamasa-Holm equation can offer, in fact, it can offer not only smooth waves, but also the waves with singularity. For Kamasa-Holm equation, we have to be a little bit careful with solutions of the initial value problem. And it turns out that one needs to control the slopes, the first derivative of the solutions, in order to get local well-poseness in the space H1 with the bounded slopes. If you look at the traveling waves, then we will find intervals for parameters for which waves are smooth, and intervals for parameters for which the waves are peaked or cusped. These are two types of singularity. For peak, it's a finite jump of the first derivative. The first derivative is still bounded. For cusped, it's an infinite jump of the first derivative. So the first derivative is unbounded. Both coexist, smooth and peaked, and both smooth and peaked waves are still constrained minimizers of energy. The energy is still defined in the space of H1. However, we are now lacking local well-posedness in H1. We need to control the slopes in the time evolution. Because of that, we have to be very careful with stability analysis. For the waves with smooth profile, it was proven that the waves are still stable because there is a momentum density which can be used to control the slopes for the waves with the smooth profiles. But for the waves with peak profiles, they are unstable in the time evolution. The perturbations do not grow in H1 because of these constrained minimization properties, but the perturbations do grow in W1 infinity, and that makes the profiles unstable. So as a summary of what this Kamasa-Holm equation can offer, it's a cartoon here with admissible range of the velocities for which smooth waves exist, something like waves with such nice profiles. Intervals for which cusped wave exists, the waves with infinite singularity for the slopes for the first derivative. And then in between, there is a point for which the wave is peaked. There is a singularity, but it's not strong. The first derivative just jumps by finite number here. And that's a state of the art for the Kamasa-Holm equation. Now, if you want to go away from these nonlinear PDEs and think about the original problems, the Euler equation, the Stokes wave, then obviously we know that there are smooth waves and there are peaked waves. Stokes himself predicted existence of the peak wave with 120 degrees at the crest here, and the existence of such solutions was proven by Toland and his collaborators. The existence of this precise 2 pi over 3 peaked singularity was proven by Plotnikov. But if we want to approximate or to understand stability problems related to such peaked profiles, then we would be running into troubles, and even approximation of such solutions would be troublesome. And so here I refer to some pictures from the paper of Sergei Dyachenko, Pavel Luzhnikov, and Alexander Korotkevich, where they studied approximations of these traveling wave solutions by using conformal coding, by using the formulas which will be the main item in my talk. And the smooth waves could be very approximated by Fourier series, but unfortunately it is very hard to get close to the peaked wave. There is always some distance from reaching the peak wave. If you look at how the velocity depends on the steepness of the wave, the picture is also quite confusing. It starts a very good monotonic function, but then it reaches a maximum point, and then it's not clear whether it's oscillate or just wind around here, but definitely there is at least one fault point here. And so this was the numerical results obtained before reaching the peak status, and there are no results for the peaked solutions. Recently, Anastasia and Sergei Dyachenko studied a lot in stability of such solid Stokes waves by using numerical methods. And this is quite good. And so from the beginning, I would like to say that I will be looking at the periodic waves, and I will be thinking about the stability problem with respect to periodic perturbations of the same period. It eliminates the problem of modulational stability, and I was very happy to see that recently the subject was booming with the proofs of modulational stability by using different techniques. And so these 4 groups, including the group of Bernard here. The point here to make is that these 4 groups used 4 different techniques to study modulational stability for Stokes waves, and only in the limit when the Stokes waves has small amplitude, so it eliminates immediately the peaked waves. What I wanted to mention is that we are going to work with the formalism which is neither in the list, not in the list. We are going to work with the formalism based still on conformal transformations, so something similar to the work of Walter Strauss, but with some modifications. And so the objective of our work is to inspect a closed system of nonlinear evolution equations, which we can obtain here to eliminate elliptic part of the problem and reduce it to Hamiltonian dynamics. And we will be particularly interested to understand transition from the smooth to singular traveling wave solutions, periodic wave solutions, and also to understand analytically stability of the periodic waves. So the system of equations we have been exploring is a generalization of what is called Babenka equation. And it was derived about 30 years ago, maybe 40 years ago, in the context of Euler equations. And it is using conformal transformation method. So the starting part is classical. We have the free surface profile here, the velocity potential, which is defined in the fluid domain with a periodic boundary condition in x direction, flat bottom at the bottom, and then the free surface here at the top, Neumann boundary conditions at the flat bottom. And on the top, we have this dynamical and kinematical, or kinematic and dynamic condition. One important thing here is that in order to make sense of the depths, we need to do some kind of normalization. And our normalization will be the zero mean constraint here. Now, with conformal transformation, we think about mapping the fluid domain to a rectangle. And the transformation is supposed to be given, expressed in terms of holomorphic function, so that for real and imaginary parts, the holomorphic function would satisfy Cauchy-Riemann equation. The domain here in the W plane becomes a rectangle, which we particularly like because we can use separation of variables and PDE techniques to solve this elliptic part of the problem explicitly. We would do still periodic boundary conditions here in the horizontal direction. We would do Neumann boundary conditions both for the potentials and also for the X part of the mapping. And we would have to define a little bit the depth of the fluid here, H, that's the depth of the fluid in W coordinate variable, may be different from H0. The difference is the mean value of the free surface. But once we have separation of variables, we know how to solve this kind of problems. And so here we can see here the difference between the two depths, which would be the mean value of the free surface here. We can do the same thing for the velocity potential because the Laplace equation is invariant under conformal transformation, so it's still the same kind of problem for the velocity potential. And with this formalism, we would define two canonical variables. One is for the velocity potential at the top surface, and the other one is the free surface, which is now mapped at the top surface in the W plane, psi and eta variables. And as it was derived 30 years ago, these equations are closed and they look like these two equations for the free surface and for the velocity potential. So in fact, the derivation can be found in the papers of Alexander Dyachenko, Kuznetsov, Spectral, Zakharov, and many other papers around this time. We particularly like the derivation in appendix of the paper of Sergei Dyachenko, Luzhnikov, and Korotkevich here. And we have followed these derivations to check that it's all consistent and correct. And so if we look at these equations, then they are local with respect to time, which is a good thing. It's a little bit quadratic here with respect to time, which makes it slightly more complicated than what we want to. But they are still non-local with respect to the spatial variable. Here, the non-local operator is a multiplicative operator in the Fourier domain, and it just expresses the wave dispersion. So for example, here, the tanh can be seen here as a mapping from X to Y variable, and that's expressed by the operator T. Obviously, this operator is not invertible. However, if it gives a zero mean value for the periodic function when it acts. And so if we restrict our consideration to periodic functions with zero mean, then we can invert this operator, but then there will be zero value for the mean value of this inverse operator. Both operators are skew adjoint in L2 spaces, and with this inverse operator with derivative, it becomes self-adjoint operator, which is one of the most important operators of this water wave theory, with the Fourier symbol n cot 10. So here, of course, the equations are slightly more complicated, but still they can be analyzed. In particular, we can think about conserved quantities, and we can think about traveling wave solutions to simplify these equations greatly. So first, for about conserved quantities, since we had this zero mean constraint in physical variable, and there is now transformation variable involved, this constraint maps to a quadratic constraint on the mean value for the free surface in the new variable u. But both parts of this quadratic constraint are constants of motion. And there are additional constants of motions. In particular, the last one is the Hamiltonian, the full energy of a water wave problem. It's encoded here. Now, if we think about traveling wave solutions, these equations becomes particularly nice. For the traveling wave solution, the quadratic part of the first equation cancels out, and we have a local linear relation between the potential, velocity potential, and the free surface. And if you substitute this relation to the second equation, it becomes what is known as a Babenko equation. I like the form of Babenko equation in this way, that the left-hand side is just a linear operator, self-adjoint operator here, and the right-hand side is just a quadratic non-local operator expressed by the same k. And the problem is Hamiltonian, so it can be formulated from the least action principle, from the variational derivative of the energy function. If we want to study existence, then we need to solve this equation, and both smooth and peaked traveling waves are supposed to give us profiles satisfying this equation. If we want stability, then we need to linearize this nonlinear equation and get a linearized operator, which is a self-adjoint operator in L2 space. And this is like a Hessian of the energy functionals defined at this profile of the traveling wave solution. If we want linearized evolution of this problem, this is a second order problem. The linearized evolution will give us a quadratic pencil related to this self-adjoint operator, which is slightly more complicated than what we want. And therefore, our first step was maybe to approach to this subject to think about the ways to simplify it, to think about the toy problem. And so the idea of the toy problem, which I'm going to present during my talk today, is to explore this traveling wave coordinate and to explore this kind of linear relationship between the two variables with the deviation here hidden in zeta variable. The first equation is invariant after this transformation in zeta variables and eta variables. And the second equation, which was long, remains long. However, in this long second equation, we can see a remarkable structure which is placed here in a frame, in a box. First, we see all the terms of the Babenko equation, which would define profile of the traveling wave without any truncation. And we can see the first order evolution, which is closed on the same surface elevation variable as the Babenko equation. And so the toy problem which I'm presenting now is that we can just cut out this discrepancy, this deviation variable zeta, completely neglect the first equation, cut out this part from the second equation, and consider the problem which is framed here in the box. And that's what is our toy model. And I'm going to simplify this toy model even more in order to be able to solve both existence and stability problem in a full analysis glory without any numerical approximation. And so this is the part where I will work with this toy model. So again, just one equation instead of two, which still keeps the same skew adjoint operator here in front of the time evolution, time derivative, and it keeps the Babenko equation with a self-adjoint operator here, KH. So now, as I promised, I would like to think about the shallow water limit when I can replace this non-local model with something like a nonlinear PDE to be able to study it. And one remarkable equation which comes immediately in the memory is the equation which is called intermediate long wave equation, which is one of the models of integrable problems, integrable systems. And that problem has a very similar non-local operator K, with the only difference that the mean value was non-zero, but was augmented in the same way that it's the same as the limit of n going to zero for all other Fourier modes, such that this operator can be expanded in a shallow water limit to be just identity plus second order derivative operator, and the identity here is removed by the Galilean transformation in a reference frame moving with the limiting wave speed, so that we have reductions of the intermediate long wave equation to the KdV equation. So here in our operator KH, we already have zero mean. We don't have to remove it. But the idea of the toy problem is that we are going to remove the limiting values for all other Fourier coefficients, subtract them out, such that the leading order will be just the second order derivative equation, so that this non-local problem is replaced by the PD. So I don't claim that there is a rigorous procedure involved here. It is basically a toy model where we can give a full mathematical analysis of the PD involved, in particular thinking overshoot beyond the smooth waves towards to the peaked wave and cusped wave. But if it offers something significant, then maybe we can reinspect the original problem and think if the same phenomena is available in the full water wave problem without this interesting trick. So if we think about this local PDE, then it shares all the properties of the original water wave equation. It has the same constraint, which is the zero mean constraint in the original variable. Now it's expressed in terms of a local operator here. Both parts of these constraints are constant of motion. In addition, there is a Hamiltonian, which is also constant of motion. And all these quantities are not very far from the conserved quantities of the Kamasa-Holm equation. So what we achieved here by doing this kind of a toy model, that we are at the level when it is not a KdV theory, but more like a level of Kamasa-Holm theory, with the quantities defined like this. So here in the main part of my talk, I'm going to present two main results on this local model, which we derived in this way. Actually, three main results. The first result is about initial value problem. We think about initial value problem, and there is still non-locality involved here. The derivative in spatial variable applies to the left. That's yes?
On your previous slide, so you have the constraint. So both, as you said, both parts of that are conserved quantities. The second one's clearly positive.
Yes.
So in the toy model, you don't have that the average of eta is zero anymore.
In fact, it's strictly negative because this is a positive quantity. So we have this mean constraint, which comes from original mean in terms of the integral of eta with respect to x. And now, because of the chain rule transformation, it becomes this additional quadratic constraint. So from here, the mean value is constant in time, but it's always equal negative to this positive quantity here, which could be considered to be momentum. So mass, momentum, and energy is the same terminology as we used to do in KdV theory. But in addition to this, there is a non-locality involved because there is still derivative here, which we need to invert. And in order to comply, in order to this is inversion, we have the zero mean constraint. So it's not zero mean constraint, we have this non-linear constraint, right?
Okay, thank you.
Okay, great. And so I wanted just to show that the origin of this non-locality, which is still remaining in this problem, that's because of this operator TH. KH is TH derivative, so if KH is replaced by second derivative, TH inverse is supposed to be replaced by first order derivative, and that's how it appears to be in the problem. But the good stuff is that since this quantity has zero mean, I can use projection operator to the subspace of L2 functions with zero mean, and on this subspace I can invert the derivative, obviously, the Fourier series inversion, and I can define uniquely the antiderivative to have also zero mean, in which case we have conserved quantity for eta, conserved quantity for derivative of eta squared, and the additional zero constraint here. In this evolutionary form, we can prove well-posedness theory quite easily because the right-hand side is a sum of two parts. The first part is local, and it is inviscid Burger's equation, solutions of which are well defined by characteristics in the space of H1 with the bounded slopes. So the Burger's equation, we always have to control the slopes. And with this non-local part, the second part, it's a bounded operator on every bounded subset in that space as well. And so by using kind of method of characteristic Duhamel principle, we can immediately end up with a local well-posedness in H1 space intersecting with the bounded slopes, bounded first derivatives. And that's a space which makes sense for peaked wave and for smooth waves, but maybe not so much for cusped wave, if we want to consider evolution of the cusped wave. Now, if we think about traveling wave solution, we don't have to use traveling wave coordinate anymore. It was already done before. And we have very explicitly the parameter for the speed of the traveling wave here encoded. What we have instead is the ODE. ODE for time-independent solution of this toy model. And that is a nice ODE which can be fully solved, fully studied. And the main principal result which I wanted to show is precisely this existence theory. The periodic waves with a normalized period of 2 pi, we always do 2 pi here for the normalization of the period, bifurcate from the unit value of the wave speed c. In that limit, the L infinity norm of the solution goes to 0. And then it always bifurcates to the right of this limit in wave speed. And there exists another remarkable value C star, here given explicitly, for which the wave remains smooth. Past the value C star, in fact, there is a non-empty interval of wave speeds for which the wave is continuous, but the first derivative is singular. It's a strongly singular with infinite jump of the first derivative, and more precisely, it has a very precise asymptotic expansion to be exactly mod U2 as comes from the ODE theory. And so if we want maybe to illustrate this with pictures, here they are. If we increment the speed parameters, then the small amplitude wave becomes strongly nonlinear and approaches, in our theory, it approaches without any problems to the peaked wave. We have no any problems, any discrepancies here. And then the dotted line, or dashed line shows the peaked wave with a finite jump of the slope. And then past this peak wave, there is a family of cusped wave with infinite jump of the slopes. And the waves exist still in an empty interval of wave speeds. So this precisely confirm or maybe generalize, or maybe just give another example of the phenomena I was talking about when I was reviewing Kamasa-Holm equation. The interval of wave speeds for which smooth waves exist, interval of wave speeds for which cusped wave exists, and then a very particular border point for which the wave is peaked. In fact, it exists in a very explicit way as a parabolic profile for that precise wave speed. So it's just for one wave speed, it is parabolic profile. What is interesting and may attract some attention that if we think about the highest, the maximal height of the wave, then for all cusped waves, the maximal height happens exactly at 1/2 c squared, which is Bernoulli law. It comes from Bernoulli law of hydrodynamics. Waves of the maximal height should have 1/2 c squared at the maximum value. Another remarkable thing is this behavior of u to the power 2/3. Since u is a variable in W plane and we use this analytical transformation, conformal mapping, but which is not fully conformal now because there is a singularity involved, still the singularity is unfolded precisely to give us a peak with 120 degrees. And so here, for the first time, we can see that maybe such things like a cusp wave, like a Stokes peaked wave, in the original Euler equations exist not just for one particular limit in wave speed, but for the whole range of the wave speeds. And the border point, it's not clear what it is sent to by conformal transformation. What is the border point which separates the family of smooth waves from the family of singular waves? Maybe it's an artifact of the toy model, but maybe it exists and one needs just to study more attentively Euler equations in this Babenko formulation. And so I will give a little bit of details, not much, about how this result can be proven. In fact, it's just ODE theory. We are lucky to have Hamiltonian ODE from Hamiltonian PDE, so it says there is a first order invariant. And with this first order invariant, we know that all orbits of ODE, they are level curves of this function of two variables. With smooth curves existing inside of separatrix loop, they give us smooth periodic waves. And cusped waves exist outside, gives us singular waves, and this parabolic wave, the peak wave, is just this separatrix curve. One important ingredient of the theory for DEs on a phase plane is the period function. That's the duration of the period of this free surface. And it is a function of the parameter C, but also a function of this level, constant level, for the function of for the first order invariant. And most important thing that it is monotonic. It is monotonically increasing with respect to C, and it is monotonically decreasing with respect to this level E, at least within the family of the smooth waves and slightly beyond the family of the smooth waves. So in fact, in order to illustrate this, I will just give a picture here from E0, that's from the center point. The period function is monotonically decreasing, passes this limiting peak wave, still monotonically decreasing until it reaches a global minimum, and then it increases. And so if we want to identify how many 2π periodic solutions exist, what we have to do is just to find a root of this period function at the level 2π. And the other dotted curve shows the same period function for larger values of C to show that it's indeed monotonically increasing with respect to C. So with this, we have an existence diagram completely. The family of smooth wave exists between the black points. The family of cusped wave exists between black point and the red point. And there is one more family here, the cusped the singular family, which we completely ignore because it doesn't bifurcate from the linear limit, so we don't need to worry about it. And so with the same kind of analysis, we can see the relevance of the peaked wave. The singularity is cancelled here in the quadrature, and the second derivative is in fact constant, so it's a parabolic profile wave. And then if the value of the level E is above the critical level, then the singularity is not cancelled. And from that singularity, by very elementary analysis, we can get back this law of U to the power 2/3. So with this, I'm going to present the last important result, which I have for the toy model, is a full understanding of stability, at least for the smooth and for the peaked wave. So for the stability analysis, we would think about something like adding a perturbation to the profile. Remember that I cut out quadratic eigenvalue problem, and now it becomes a linear eigenvalue problem, or in other words, first order with respect to time. Evolution is well defined here by linearized Bobenko operator, which is here, self-adjoint operator. Then we have this constraint of the theory, which gives us a proper orthogonality of the perturbation to this local part, so that the antiderivative is again well defined. But because we have conservation quantity for this, we can always complement with two constraints. So requiring both the mean value to be just zero and the perturbation to be orthogonal to the second derivative, just zero. And that's just two fixed mass and the fixed momentum, the same concept, which is very useful in the orbital stability theorem. With this, we have the following theorem. For the entire family of the smooth periodic waves, we are guaranteeing linear orbital stability, meaning that for any initial date H1 with these two constraints, there exists a unique solution staying in H1, such that this unique solution is not growing relative to the translation of the original periodic wave. So this is a derivative with respect to space. It's a translational mode, and the translational mode is controllable. It cannot grow faster than the linear function, but then the perturbation is defined relative to this translational mode, which is very typical for the orbital stability concept. The idea of, okay, before that, a few remarks are in order. So first of all, we can do spectral stability with the same level. Linear stability, in fact, implies spectral stability here. For spectral stability, we would have an eigenvalue problem, and the entire spectrum is a subset of a purely imaginary line. What is interesting about this problem is that if we now differentiate this, we can reformulate it in the form which appears in the work of Stanislav and Stefanov in 2016. I think they were looking at the different examples, but now with this toy model, we have a very natural example where, for applications of this stability theory for this strange, interesting eigenvalue problem. On the other hand, linear stability doesn't apply nonlinear stability because we are using energy quantity to control perturbations in H1, like it was here in the theorem, the norms of H1 given, while the slopes are not controllable from the energy. And I don't know any momentum quantity which could be useful here to control the slopes. If it exists, then we can upgrade it for the nonlinear stability analysis, but so far no luck. Then I think I can prove also instability of the peaked wave by using the ideas we were developing very recently in the context of other fluid models, but so far we have not written this part up. But what is interesting is that if you are really interested in stability of the singular waves, the cusp wave with this law of U to the power 2/3, then there is no theory which can be applied to those, because the cusp wave doesn't exist in the space of H1 with bounded slopes. And therefore, well-posedness is lacking in order to identify, to even understand stability of cusp wave. So here I will just mention a little bit of how easy to prove the stability theory if we have such nice toy model as we have here. In fact, what we have to do is to operate with the energy quadratic form, which is related to this self-adjoint operator, sum of the two terms here. It's a constant with respect to the time evolution. If it is positive definite, we have immediately Lyapunov stability theory. Unfortunately, it's not positive definite, but the spectrum of it can be fully understood. First of all, it's a Sturm-Liouville type problem in a periodic domain. The spectrum is purely point consisting of isolated eigenvalues, 0 in the spectrum because of translational mode. But the second homogeneous solution of this operator is given precisely by the derivative of the family with respect to this level of energy, the level of the first order invariant used in existence theory. And so, since this is not 2-pi periodic, we know that 0 is a simple eigenvalue, but we also, from the monotonicity of this quantity, we have immediately the theorem, criterion to guarantee existence of 2 negative eigenvalues in the spectrum. So, if you go back to the quadratic form, no, there are 2 negative eigenvalues, so we cannot use it as a Lyapunov function. But there are 2 constraints, which are fixed mass and fixed momentum. And with these 2 constraints, by simple calculus in constrained spaces, we can prove that the operator has no negative eigenvalue and has a simple 0 eigenvalue. The criteria for which is the monotonicity of the mass. It should be monotonically decreasing. But this is, in fact, we can prove. Again, ODE theory can be used to prove it rigorously. These numerics just illustrate monotonicity of the mass with respect to mass is negative and it's monotonically decreasing to the negative side. And it's valid for for the entire family of the smooth waves. And so with this, then the rest is just a decomposition. So initial data is supposed to be orthogonal to 2 constraints. And then we decompose it in a neutral mode and the remainder term and require diagonality of the remainder term to the neutral mode. Then now quadratic form is fully coercive with respect to this perturbation. And quadratic form is conserved in time. And quadratic form is bounded in the space of H1, from which we immediately have H1 stability bound of the linear theory. And so with this, I think I finished my part on the toy model, and in the rest of my time, I can explain some other exciting features of this Babenka equation and maybe linearized Babenka equation outside of the toy model. So I'm back to the Babenka equation in with a full dispersion here, and we can inspect, of course, this Babenka equation for any h, but because it's an undergraded project, it had limited time. So we inspected this Babenka equation in the deep water limit. It is a non-local equation in the deep water limit, but non-locality is a sort of well-known. It's the derivative and Hilbert transform, which is very well defined with respect to Fourier series. So in this model, the model can be rewritten in this case, in this way. And one of the first results would be immediately small amplitude expansion. It's always the first result I try when I have periodic waves. In this way, we can immediately illustrate this bifurcation from the unit speed c, bifurcation to the right with the amplitude of the wave here quadratically expanding. And apparently this result was written back to 1880. So it's an old result from the time of Stokes. What is more interesting is to think about the limiting wave. So to think about the cusped wave for which eta reaches the highest, the maximal height at 1/2 c squared. In this way, I found interesting to rewrite the problem with respect to deviation from this maximal height. The deviation will be zeta, will be positive definite quantity. And when we do this, we are canceling the non-local linear part of the problem. That's a remarkable phenomenon. So as a result, the entire Babenka equation can be written as a fixed point equation. Zeta is equal to a certain operator, which is just defined in terms of a quadratic part with plus some constant. And so from analysis of this equation, we can prove a couple of results, which are sort of well agreed with a well-known theory, asymptotic theory, but I think these results were never derived by using Babenka equation. The first result is the following. If we think about the wave being singular in a fractional way, alpha is between 0 and 1, then we shall try to inspect what kind of powers of alpha this fixed point equation admits. And we can prove that this fixed point equation admits only one power of alpha, which is exactly 2/3. No other powers of alpha are admitted by this fixed point equation around the peak, around the singularity. And that is apparently in agreement with all the results I already mentioned. But then we can go further. We can think, okay, if the wave is a singular and we add a perturbation which should be smoother than this, but still in a fractional power, something between 2/3 and 2, then can we find a very precise value for beta, for which the perturbation is defined? And then in this way, we can derive the following transcendental equation, which coincide explicitly with the equation derived by Grant by using Euler equation. At that time, 73, Grant did not use Babenko equation. So we have effectively recovered exactly the same equation as in a Grant paper, but simply by analyzing all admissible singular solutions of this Babenko equation. So unfortunately, in that theory, neither constant could be well defined. A, B, and even the C here in the equation C cannot be uniquely defined. They are defined from a non-local problem. So the singularity analysis, which is sufficient to identify correct powers, are not capable to give us a very explicit formula for A, B, or for C. Other things we can think is about linearization and stability theory. The linearized Babenko equation is still a self-adjoint operator. And here, if we are in the small amplitude expansion case, we immediately see that this operator is close to a constant coefficient operator with spectrum being given by Fourier modes. Zero Fourier mode is located at negative eigenvalue -1. First Fourier modes, cosine and sines, give double eigenvalue 0. Higher Fourier modes give positive eigenvalues. So if we now bifurcate from this limit along the family of periodic wave solutions, then the 0 eigenvalue is split, and it remains as a simple 0 eigenvalue because of translational symmetry, but it also generates small negative eigenvalue. And this value is precisely in agreement with numerical results published in a paper of Sergei Dyachenko and Simonov. And so this is also quite good. Figure 8 for modulation of stability. I said that I'm not going to do it, but in fact, it was the first thing which we recovered by using Babenko equation and this second order time evolution equation, by using exactly the same ideas and expansions. In fact, this figure 8 is related to the Fourier modes which sit here and split to the negative eigenvalue. And so our slopes here are in a full agreement with the recent results, and I think the recent results are just justification of some old results. So with this, I think I will finish my talk. I think it's the right time with a short summary. So I'm sailing today this toy model, which is the first order evolution equation closed for the surface elevation as a truncation of the second order evolution equation. It has exactly the same solutions as the traveling waves, and it makes stability analysis extremely simple because it reduces to the linear eigenvalue problem instead of quadratic eigenvalue problem. Again, justification of this toy model is questionable. We haven't thought about it, but it's quite promising model in a full glory with the full dispersion. But in addition to this, in this toy model for the shallow water limit, we have our main results that continuous families exist not only for smooth waves, but also for cusped waves, separated by single peaked wave in W plane, right? In a pre-image plane compared to the physical domain. The smooth waves are linearly stable in the time evolution. Peaked wave is linearly unstable. No results for cusped wave could be unless we can push up the well-Posner theory. And the well-Posner theory is well formulated in the same space as Wick's theory for Kamasa-Holm equation. So thank you very much for your attention.
Stop the video.